Vector space. In mathematics, physics, and engineering, a vector space, also called a linear space, is a set of objects called vectors, which may be added together and multiplied scaled by numbers called scalars. Scalars are often real numbers, but some vector spaces have scalar multiplication by complex numbers, or generally by a scalar from any mathematic field. The operations of vector addition and scalar multiplication must satisfy certain requirements, called vector axioms, listed below in SS notation and definition. To specify whether the scalars in a particular vector space are real numbers or complex numbers, the terms real vector space and complex vector space are often used. Certain sets of Euclidean vectors are common examples of a vector space. They represent physical quantities such as forces, where any two forces of the same type can be added to yield a third, and the multiplication of a force vector by a real multiplier is another force vector. In the same way that in a more geometric sense, vectors representing displacements in the plane or three-dimensional space also form vector spaces. Vectors in vector spaces do not necessarily have to be arrow-like objects as they appear in the mentioned examples. Vectors are regarded as abstract mathematical objects with particular properties, which in some cases can be visualized as arrows. Vector spaces are the subject of linear algebra and are well characterized by their dimension, which, roughly speaking, specifies the number of independent directions in the space. Infinite dimensional vector spaces arise naturally in mathematical analysis as function spaces, whose vectors are functions. These vector spaces are generally endowed with some additional structure such as a topology, which allows the consideration of issues of proximity and continuity. Among these topologies, those that are defined by a norm or inner product are more commonly used, being equipped with a notion of distance between two vectors. This is particularly the case of Banach spaces and Hilbert spaces, which are fundamental in mathematical analysis. Historically, the first ideas leading to vector spaces can be traced back as far as the 17th century's analytic geometry, matrices, systems of linear equations, and Euclidean vectors. The modern, more abstract treatment, first formulated by Giuseppe Peano in 1888, encompasses more general objects than Euclidean space, but much of the theory can be seen as an extension of classical geometric ideas like lines, planes, and their higher dimensional analogues. Today, vector spaces are applied throughout mathematics, science, and engineering. They are the appropriate linear algebraic notion to deal with systems of linear equations. They offer a framework for Fourier expansion, which is employed in image compression routines, and they provide an environment that can be used for solution techniques for partial differential equations. Furthermore, vector spaces furnish an abstract, coordinate-free way of dealing with geometrical and physical objects, such as tensors. This in turn allows the examination of local properties of manifolds by linearization techniques. Vector spaces may be generalized in several ways, leading to more advanced notions in geometry and abstract algebra. This article deals mainly with finite-dimensional vector spaces. However, many of the principles are also valid for infinite-dimensional vector spaces. Motivating examples. Two typical vector space examples are described first. First example, arrows in the plane. The first example of a vector space consists of arrows in a fixed plane, starting at one fixed point. This is used in physics to describe forces or velocities. Given any two such arrows, V and W, the parallelogram spanned by these two arrows contains one diagonal arrow that starts at the origin, 2. This new arrow is called the sum of the two arrows and is denoted V plus W. In the special case of two arrows on the same line, their sum is the arrow on this line whose length is the sum or the difference of the lengths, depending on whether the arrows have the same direction. Another operation that can be done with arrows is scaling. Given any positive real number a, the arrow that has the same direction as V but is dilated or shrunk by multiplying its length by a is called multiplication of V by a. It is denoted av. When A is negative, f is defined as the arrow pointing in the opposite direction instead. The following shows a few examples. If it equals 2, the resulting vector A has the same direction as W but is stretched to the double length of W, right image below. Equivalently, 2 is the sum W plus W, 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 W. Moreover, 1 equals V has the opposite direction and the same length as the blue vector pointing down in the right image. Second example, ordered pairs of numbers. Notation and definition, alternative formulations and elementary consequences. Vector addition and scalar multiplication are operations satisfying the closure property U plus V and AB are in V for all and in F and U V in V. Some older sources mention these properties as separate axioms. In the parlance of abstract algebra, the first four axioms are equivalent to requiring the set of vectors to be an abelian group under addition. The remaining axioms give this group an F-module structure. In other words, there is a ring homomorphism, F from the field F into the endomorphism ring of the group of vectors. Then scalar multiplication A is defined as FAV. There are a number of direct consequences of the vector space axioms. Some of them derive from elementary group theory applied to the additive group of vectors. For example, the zero vector 0 of V and the additive inverse V of any vector V are unique. Further properties follow by employing also the distributive law for the scalar multiplication. For example, V equals 0 if and only if A equals 0 or V equals 0. History. Vector spaces stem from affine geometry via the introduction of coordinates in the plane or three-dimensional space. Around 1636, French mathematicians René Descartes and Pierre de Fermat founded analytic geometry by identifying solutions to an equation of two variables with points on a plane curve. To achieve geometric solutions without using coordinates, Bolzano introduced, in 1804, certain operations on points, lines, and planes, which are predecessors of vectors. Mobius 1827 introduced the notion of barycentric coordinates. Velivitis 1833 introduced the notion of a point, i.e., an oriented segment, one of whose ends is the origin and the other one a target. Vectors were reconsidered with the presentation of complex numbers by Argand and Hamilton and the inception of quaternions by the latter. They are elements in R2, and R4 treating them using linear combinations goes back to Laguerre in 1867, who also defined systems of linear equations. In 1857, Cayley introduced the matrix notation, which allows for a harmonization and simplification of linear maps. Around the same time, Grassmann studied the barycentric calculus initiated by Mobius. He envisaged sets of abstract objects endowed with operations. In his work, the concepts of linear independence and dimension, as well as scalar products, are present. Actually, Grassmann's 1844 work exceeds the framework of vector spaces, since his considering multiplication, too, led him to what are today called algebras. Italian mathematician Pino was the first to give the modern definition of vector spaces and linear maps in 1888. An important development of vector spaces is due to the construction of function spaces by Henry Lebesgue. This was later formalized by Banach and Hilbert around 1920. At that time, algebra and the new field of functional analysis began to interact, notably with key concepts such as spaces of p-integrable functions and Hilbert spaces. Also at this time, the first studies concerning infinite-dimensional vector spaces were done. Examples. Coordinate space. The simplest example of a vector space over a field F is the field F itself, as it is an abelian group for addition, a part of requirements to be a field. Equipped with its addition, it becomes vector addition, and multiplication, it becomes scalar multiplication. More generally, all n-tuples sequences of length n, aon at wo, and of elements ai of F form a vector space that is usually denoted Fn and called a coordinate space. The case n equals 1 is the above-mentioned simplest example. in which the field F is also regarded as a vector space over itself. The case F equals R and N equals 2 so R2 was discussed in the introduction above. Complex numbers and other field extensions. Function spaces. Functions from any fixed set O to a field F also form vector spaces by performing addition and scalar multiplication pointwise. That is, the sum of two functions f and g is the function f plus g given by f plus g, w equals f, w plus g, w, and similarly for multiplication. Such function spaces occur in many geometric situations, when O is the real line or an interval, or other subsets of R. Many notions in topology and analysis, such as continuity, integrability, or differentiability, are well behaved with respect to linearity. Sums and scalar multiples of functions possessing such a property still have that property. Therefore, a set of such functions are vector spaces. They are studied in greater detail using the methods of functional analysis. See below. Algebraic constraints also yield vector spaces. The vector space fx is given by polynomial functions. F x equals r0 plus rho(x) plus rn1 plus rnxn, where the coefficients are 0. Rn Rnf. Linear equations. Space of derived units. Basis and dimension. Bases allow one to represent vectors by a sequence of scalars called coordinates or components. A basis is a set B equals by I of vectors by, for convenience often indexed by some index set I, that spans the whole space and is linearly independent. Spanning the whole space means that any vector V can be expressed as a finite sum called a linear combination of the basis elements, where the AC are scalars, called the coordinates or the components of the vector V with respect to the basis B and bit k equals 1. For example, the coordinate vectors eon equals 1, 0, 0, etwo equals 0, 1, 0, 0, 2n equals 0, 0, 0, 1 form a basis of Fn, called the standard basis, since any vector zone x2, xn can be uniquely expressed as a linear combination of these vectors. Zone x2, xn equals zonion 0, and rho equals zonion 0, o, rho, 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 0 plus x2 0, 1 0, 0, 0, 0 plus xn 0, 0, 1 equals zonion plus x2 etwol plus xn. The corresponding coordinates zone, x2, xn are just the Cartesian coordinates of the vector. Every vector space has a basis. This follows from Zorn's lemma, an equivalent formulation of the axiom of choice. Given the other axioms of Zermelo-Fraenkel set theory, the existence of bases is equivalent to the axiom of choice. The ultrafilter lemma, which is weaker than the axiom of choice, implies that all bases of a given vector space have the same number of elements, or cardinality cf. dimension theorem for vector spaces. It is called the dimension of the vector space, denoted by dim_v, if the space is spanned by finitely many vectors. The above statements can be proven without such fundamental input from set theory. The dimension of the coordinate space Fn is n, by the basis exhibited above. The dimension of the polynomial ring fx introduced above is countably infinite. A basis is given by 1 x x2. A fortiori, the dimension of more general function spaces, such as the space of functions on some bounded or unbounded interval, is infinite. Under suitable regularity assumptions on the coefficients involved, the dimension of the solution space of a homogeneous ordinary differential equation equals the degree of the equation. For example, the solution space for the above equation is generated by Ex and Zx. These two functions are linearly independent over R, so the dimension of this space is 2, as is the degree of the equation. A field extension over the rationals Q can be thought of as a vector space over Q by defining vector addition as field addition, defining scalar multiplication as field multiplication by elements of Q, and otherwise ignoring the field multiplication. The dimension or degree of the field extension K over Q depends on A. If A satisfies some polynomial equation with rational coefficients Qn. More precisely, it equals the degree of the minimal polynomial having as a root. For example, the complex numbers C are a two-dimensional real vector space generated by 1 and the imaginary unit I. The latter satisfies a 2 plus 1 equals 0, an equation of degree 2. Thus, C is a two-dimensional R vector space and, as any field, one-dimensional as a vector space over itself, C. If it is not algebraic, the dimension of K over Q is infinite. For example, for A equals P there is no such equation. That is, P is transcendental. Linear maps and matrices. Matrices. Eigenvalues and eigenvectors. Endomorphisms. Linear maps F, V, V are particularly important since in this case vectors V can be compared with their image under F, Fv. Any non-zero vector V satisfying LV equals Fv, where L is a scalar, is called an eigenvector of F with eigenvalue L. Equivalently, V is an element of the kernel of the difference FL *ID where ID is the identity map VV. If V is finite dimensional, this can be rephrased using determinants. F having eigenvalue L is equivalent to 2 def L asterisk ID equals 0. By spelling out the definition of the determinant, the expression on the left-hand side can be seen to be a polynomial function in L, called the characteristic polynomial of F. If the field F is large enough to contain a zero of this polynomial, which automatically happens for F algebraically closed, such as F equals C any linear map, the vector space V may or may not possess an eigenbasis, a basis consisting of eigenvectors. This phenomenon is governed by the Jordan canonical form of the map. The set of all eigenvectors corresponding to a particular eigenvalue of F forms a vector space known as the eigenspace corresponding to the eigenvalue and F in question. To achieve the spectral theorem, the corresponding statement in the infinite dimensional case, the machinery of functional analysis, is needed. See below. Basic constructions. Fractions. In addition to the above concrete examples, there are a number of standard linear algebraic constructions that yield vector spaces related to given ones. In addition to the definitions given below, they are also characterized by universal properties, which determine an object X by specifying the linear maps from X to any other vector space. Subspaces and quotient spaces. Direct product and direct sum. Tensor product. The tensor product V, Fw or simply V, W of two vector spaces V and W is one of the central notions of multilinear algebra, which deals with extending notions, such as linear maps, to several variables. A map G, V x W x is called bilinear if G is linear in both variables V and W, that is to say, for fixed W the map VGV. W is linear in the sense above, and likewise for fixed V. The tensor product is a particular vector space that is a universal recipient of bilinear maps G as follows. It is defined as the vector space consisting of finite formal sums of symbols called tensors. Von 1 plus V2, W2 plus Vn, Wn subject to the rules asterisk V, W equals asterisk risk, asterisk V, W equals V, A asterisks to risks. W where is a scalar, Von plus V2, W equals Von, W plus V2, W and V1 plus W2 equals V, 1 plus V, W2. These rules ensure that the map F from the Vxw to Vw that maps a tuple W to Vw is bilinear. The universality states that given any vector space X and any bilinear map G, Vxwx, there exists a unique map U, shown in the diagram with a dotted arrow, whose composition with F equals GUV, W equals GV, A GV, A GV, A GV, W. This is called the universal property of the tensor product, an instance of the method much used in advanced abstract algebra to indirectly define objects by specifying maps from or to this object. Vector spaces with additional structure. Normed vector spaces and inner product spaces. Topological vector spaces. Banach spaces. Hilbert spaces. Algebras over fields. General vector spaces do not possess a multiplication between vectors. A vector space equipped with an additional bilinear operator defining the multiplication of two vectors is an algebra over a field. Many algebras stem from functions on some geometrical object, since functions with values in a given field can be multiplied pointwise. These entities form algebras. The Stone-Weierstrass theorem, for example, relies on Banach algebras, which are both Banach spaces and algebras. Commutative algebra makes great use of rings of polynomials in one or several variables introduced above. Their multiplication is both commutative and associative. These rings and their quotients form the basis of algebraic geometry because they are rings of functions of algebraic geometric objects. Another crucial example are Lie algebras, which are neither commutative nor associative, but the failure to be so is limited by the constraints x. Y denotes the product of x and y, x, y equals y, x anticommutativity, and x, y, z plus y, z, x plus z, x, y equals 0 Jacobi identity. Examples include the vector space of n by n matrices with x, y equals xyx, the commutator of two matrices, and R3 endowed with the cross product. The tensor algebra TV is a formal way of adding products to any vector space V to obtain an algebra. As a vector space, it is spanned by symbols called simple tensors. Von, V2, Vn, where the degree n varies. The multiplication is given by concatenating such symbols, imposing the distributive law under addition, and requiring that scalar multiplication commute with the tensor product, much the same way as with the tensor product of two vector spaces introduced above. In general, there are no relations between Von, V2 and V2, Von. Forcing two such elements to be equal leads to the symmetric algebra, whereas forcing Von, V2 equals V2, Von yields the exterior algebra. When a field, F is explicitly stated, a common term used is F-algebra. Applications. Vector spaces have many applications as they occur frequently in common circumstances, namely wherever functions with values in some field are involved. They provide a framework to deal with analytical and geometrical problems, or are used in the Fourier transform. This list is not exhaustive. Many more applications exist, for example, in optimization. The minimax theorem of game theory stating the existence of a unique payoff when all players play optimally can be formulated and proven using vector spaces methods. Representation theory fruitfully transfers the good understanding of linear, algebra, and vector spaces to other mathematical domains such as group theory. Distributions. Fourier analysis. Differential geometry. The tangent plane to a surface at a point is naturally a vector space whose origin is identified with the point of contact. The tangent plane is the best linear approximation or linearization of a surface at a point. Even in a three-dimensional Euclidean space, there is typically no natural way to prescribe a basis of the tangent plane, and so it is conceived of as an abstract vector space rather than a real coordinate space. The tangent space is the generalization to higher dimensional differentiable manifolds. Riemannian manifolds are manifolds whose tangent spaces are endowed with a suitable inner product. Derived therefrom, the Riemann curvature tensor encodes all curvatures of a manifold in one object, which finds applications in general relativity, for example, where the Einstein curvature tensor describes the matter and energy content of spacetime. The tangent space of a Lie group can be given naturally the structure of a Lie algebra and can be used to classify compact Lie groups. Related structures. Vector bundles. A vector bundle is a family of vector spaces parametrized continuously by a topological space X. More precisely, a vector bundle over X is a topological space E equipped with a continuous map P Ex such that for every X in X, the fiber P1 is a vector space. The case dim V equals 1 is called a line bundle. For any vector space V, the projection XXVX makes the product XXV into a trivial vector bundle. Vector bundles over X are required to be locally a product of X and some fixed vector space V. For every X in X, there is a neighborhood U of X such that the restriction of P to P1U is isomorphic. For example, the Mobius strip can be seen as a line bundle over the circle sown by identifying open intervals with the real line. It is, however, different from the cylinder sown XR because the latter is orientable whereas the former is not. Properties of certain vector bundles provide information about the underlying topological space. For example, the tangent bundle consists of the collection of tangent spaces parametrized by the points of a differentiable manifold. The tangent bundle of the circle sown is globally isomorphic to sown XR since there is a global non-zero vector field on sown. In contrast, by the Harry-Ball theorem, there is no tangent vector field on the two-sphere S2, which is everywhere non-zero. K-theory studies the isomorphism classes of all vector bundles over some topological space. In addition to deepening topological and geometrical insight, it has purely algebraic consequences, such as the classification of finite-dimensional real division algebras, R, C, the quaternions H and the octonions O. The cotangent bundle of a differentiable manifold consists, at every point of the manifold, of the dual of the tangent space, the cotangent space. Sections of that bundle are known as differential one forms. Modules. Modules are to rings what vector spaces are to fields. The same axioms applied to a ring are instead of a field F yield modules. The theory of modules, compared to that of vector spaces, is complicated by the presence of ring elements that do not have multiplicative inverses. For example, modules need not have bases, as the Z module that is, abelian group Z/2Z shows. Those modules that do, including all vector spaces, are known as free modules. Nevertheless, a vector space can be compactly defined as a module over a ring which is a field, with the elements being called vectors. Some authors use the term vector space to mean modules over a division ring. The algebrogeometric interpretation of commutative rings via their spectrum allows the development of concepts such as locally free modules, the algebraic counterpart to vector bundles. Affine and projective spaces. Roughly, affine spaces are vector spaces whose origins are not specified. More precisely, an affine space is a set with a free transitive vector space action. In particular, a vector space is an affine space over itself by the map Vxv plus V. If W is a vector space, then an affine subspace is a subset of W obtained by translating a linear subspace V by a fixed vector X. W. This space is denoted by X plus V. It is a coset of V in W and consists of all vectors of the form X plus V for V. An important example, X equals B, generalizing the homogeneous case above, which can be found by setting V equals 0 in this equation. The space of solutions is the affine subspace X plus V, where X is a particular solution of the equation, and V is the space of solutions of the homogeneous equation, the null space of A. The set of one-dimensional subspaces of a fixed finite-dimensional vector space V is known as projective space. It may be used to formalize the idea of parallel lines intersecting at infinity. Grassmannians and flag manifolds generalize this by parametrizing linear subspaces of fixed dimension K and flags of subspaces, respectively.